Hi, William.
Hello.
Hello.
Hi.
Hi.
Good to see you again.
Hola, buenas noches. Good night.
Hello.
Hello, William.
Well, good evening, everyone. We are going to wait a few minutes for people to come in. But yeah, this is going to be the custom review for machine learning. So uh, be away for one more minute, but the ML capstone exam review session, and if I understand correctly, the capstone exam is in like March or something. Yeah, so hopefully this review session will help you prepare or help you know what you should be preparing. And yeah, so if anyone wants to turn their phone, first of all, that would be nice. It's not really at people's faces and gauge if you're confused, bored, or so on. So just like a regular can't or don't want to, it's also kind of late at night, right? So I understand. Yeah, I guess we'll just start and but we can start anyways. So today's session, we're going to be doing a review of the material that was in the machine learning course, and that's going to be on the capstone exam. So I can't guarantee you that all these topics will be on the capstone exam, and I can't guarantee you that everything that is on exam will be included in here, but this should be like overview for what you should know for this exam. So if you're solid on these things, then you should be able to do well. And other than that, you should just continue to study the materials that you have for that machine learning course. So the structure of this is that basically I'm going to be discussing about what you need to know for each component of the course. And I have a lot of polls that I'll be asking you a question and then asking you to fill out the polls so I can see if you are if you have confusion about it or not. So if you don't turn your camera on, at least please participate because that's like the main way that you're going to get something out of this review session, I think. Okay, so there's a lot of topics to cover today, and I probably won't get through all of it, but I will try. So first of all, we have learning. We have three main components of this course, which is supervised learning, unsupervised learning, and reinforcement learning. All right, so the first one is actually quite a lot of material. There's linear classification, kernel methods, and neural networks. So those are themselves each comprise like maybe a question on each is something you might be able to expect from the capstone exam. There's unsupervised learning, which is a few maybe smaller topics. So you can also expect a question on those. There's some reinforcement learning, and there will probably be a question on this stuff, like maybe one question. So that might be like a typical breakdown of the exam, at least from previous iterations, that there's quite a bit of this supervised learning, maybe a little bit of this, and one reinforcement learning question. So that might be something you can expect from the exam. Okay, so supervised versus unsupervised learning. A lot of these things you need to know the concepts, and sometimes you might not need to know the specifics. So here I would know that the supervised learning has to do with labeled data usually, and you're usually learning to predict labels given training examples from your labeled data, right? Versus unsupervised learning, you don't have any labels on your data, you're just giving like covariates X without the Y's, and then you want to infer some structure about it, like learning the mixture model, fitting mixture model to this unsupervised data or clustering the data. So these are two different, a few different use cases, and at a high level, you should know which problems correspond to which supervised or unsupervised learning task. All right, so linear classification, you need to know about hyperplanes. And by hyperplanes, I just mean these functions of the form theta.x. Oops. Right. There's a lot of lag in this transmission, huh? You'll need to know about this this decision boundary. And also, if anyone has any issues, like my Zoom says my internet is unstable, please let me know if my internet is actually unstable and if you just can't hear me or anything like that. It's a bit of lag, thank you. So, unfortunately, I cannot do anything about that, but I hope it will clear up soon. Yeah, I don't think I can do anything about that. But yeah, please type something in the chat or just unmute yourself and talk. And like if I'm not seeing the chat, if you have any questions about anything. So basically, what the linear classifier. Okay, that's good. Thank you. Can you hear me fine? That's very good. So this linear classifier is theta.x, and what you do is you say, okay, I have a linear function, let's say theta.x plus theta naught, and then I'm going to say if it's greater than or equal to 1, then I classify as plus 1, and if it's less, sorry, made a mistake already. If it's greater than 0, I classify as plus 1, and if it's less than 0, I classify as negative 1, right? So this is a linear classifier, and it induces a certain decision boundary, which is basically the line along which you don't really have a well-distinguished classifier, right? So usually we just say as a convention that if your point lies directly on this line, then you classify it as incorrectly. That's kind of just the generic way to define it. So, and I didn't say it before, but obviously your goal is to match the y labels, which are plus, minus 1, right? So it's also good to know that multiplying this theta and theta naught, if you multiply the parameters by -1, then you're going to actually flip the direction of your decision boundary, right? So what I say here is that if you have a decision boundary like this is your line, theta.x plus theta naught equals 0. Maybe you classify these as plus and these as negative, right? So if you take the theta and theta naught are like, say theta prime and theta naught prime are equal to the negative of theta naught, then you end up flipping this decision boundary. So it's going to be negative and plus. So this is just a feature of linear classifiers that you can see directly from the definition, right? And that's just the definition as classifying via the sign of the linear function. So, and another thing that you should know is how you might want to draw a decision boundary. So you should use the fact that this theta is the normal vector to the decision boundary, right? So if I'm given some sort of theta and I want to know the decision boundary that's associated with that theta, then let's say if theta goes, if this is theta, if theta goes that way, then theta is going to be normal to the decision boundary. So if there's no, let's say there's no theta naught term, no theta 0 term, then it's going to be normal to the decision boundary. So this should be the decision boundary. Decision boundary. Boundary. This means boundary. Right, and you would classify points that are in the direction of theta as 1. That's just kind of the definition of this classifier, because it looks at the sort of correlation, you might say, with theta, and then it says it's 1 if it's positively correlated and -1 otherwise. So this stuff would be considered as plus and this would be considered as minus. Right. So now I have a question for you, and I'm going to send you a link to a Google form, which I hope it works. So my question to you is, I have this theta, which is theta equals 1, 2, so x is 1 and theta, y is 2. And I want to know which of these corresponds to the decision boundary and the correct classification rule. So I'm saying that the shaded region is where I would classify as +1. So it's where theta dot x would be, where it would be positive. So if you can fill that out, then this would be great. And as usual, let me know if anything's unclear. So, so I'm gonna wait for maybe a minute or two. Maybe 30 seconds. We have most of the people. Okay, let's go over this question. um, yeah, so since most of you put down the correct answer, which is 1. So why is 1 correct answer? Well, I said that this decision boundary should be normal to theta, which means that they should form a right angle, right? So if you draw theta on this one, it should like be like that. That's what theta is, right? It's 1, 2. And then that's going to be normal, right? And then you have to know, okay, which direction do you classify as 1? You classify the points that are in the same direction as theta as 1. So that's why this shaded region is classified as 1. So that's why it's 1 and not 2. I think the other common response that I got was 4. But so 4 classifies in kind of the correct direction, but it's not the like geometrically correct, because here this is theta, right? But the decision boundary is orthogonal to theta. So in this case, it doesn't form a right angle. Okay, so now let's continue. So here's some more information that you might want to know about linear classifiers. If if you have a linear classifier that's associated with theta, which means you have a decision boundary and a decision rule, then there are actually infinitely many parameterizations of the classifier, right? So if here we say that if theta dot x is greater than 0, so if you have a decision boundary which is governed by theta, then actually c theta, if c is positive, will have the same decision boundary associated with it, right? And you can see that because I didn't specify the norm of theta, I just specified that the direction determines the decision boundary. So if you only consider theta to have a specific norm, like norm 1, then this decision rule is uniquely determined, right? Because then if theta is a certain parameter, then other theta with different norm, with the same norm, will not induce the same decision boundary unless they are the negative, but then that one will have the opposite signs, right? So that's why I say here that theta and theta, negative theta lead to the same decision boundary, but they don't have the same decision rule associated with them. Any questions? So these are some distinctions that you can kind of figure out yourself if you know the fundamentals, and I think the fundamentals are quite important, so that's why I'm spending a bit more time on this type of material. Okay, so I have another question for you, and this one I will send you a link to. So there's this question. I have this diagram here. My first question here is asking what's the error of the best linear classifier of the form sine of theta dot x. So there's no intercept term, right? Usually sometimes you have a theta naught. Here I just have theta dot x. So the second question is, okay, what happens when you put in theta naught? The third question is, okay, look at this orange decision boundary, right? And say that it classifies everything above it as red. Then how many parameterizations of the boundary are there? And then the last question is, okay, what happens when you flip the labels of all points? What does that do for the error? Remember, the error is the fraction of misclassified points. So there are 6 points. If you misclassify 2 of them, then your error would be 1/3. So I'll give you a few minutes or as long as you need for this one. This one's a little longer. So I have about half the responses right now. So take your time. I think maybe 2 or 3 minutes. So maybe if you could finish up in a minute, or let me know if you want more time than that. You can send me a chat if you want more time, or otherwise I'll be probably moving on in a minute. Yeah. Okay. How about 20 seconds? And then I'll talk about it. Okay. Uh, yeah, I'm going to discuss now. If you didn't finish, that's okay. Yeah, so the first question was actually pretty tricky. So, I think a lot of you thought that, okay, there's the best linear classifier of this that's of the form sine of theta dot x. I think a lot of you recognize that it has to pass through the origin, right? Because it doesn't have a intercept term, so you can't have shifted lines like this orange line. So this orange line actually is not of the form sine theta dot x, right? So what I think is a lot of you were thinking of something like this type of decision boundary, right? So this gives you half the points are classified correctly, half them are incorrect. So a lot of you said 1/2, but if you look more closely, there's a decision boundary that's of this form. Well, make it pass through the origin, but it's like this decision boundary, right? So you classify this as a -1, and then this is +1. So you've only misclassified these 2 points. So actually the answer here is 1/3. The next question, it seemed to be pretty easy for you, which is good. This one is 0. There's no arrow for this best linear classifier of this particular form, and you can also say that this orange classifier here is, in fact, one such classifier that achieves 0 error. How many parameterizations of this decision boundary are there? Well, I actually did not specify the norm of this theta star and theta not star. So I didn't say that has to be a certain norm or anything like that. So from the discussion that I had on the previous slide, there are actually infinitely many parameterizations of this rule. So if you multiply theta star, theta not star by any constant that's non-negative, or any positive constant, then it'll give you the same decision boundary and the same decision rule. So there are actually infinitely many such parameterizations. And the last question says, okay, what's the error if you flip all the labels? Yeah, so if you understand that this orange line has error 0, according to what I gave you, where classifying above this boundary here is red, which matches the points, and classifying underneath it is blue, then if you flip the labels of every point, then every point that you originally classified as correctly will be classified incorrectly. So the error rate should be 1 now. So most of you got that. Okay, so don't worry if you don't get all the answers to these questions. This is more like a test to see if you know or what you need to review more. So it's also a test. It's also like a way to show you what might potentially be tested on the exam.
Sorry, just to be sure, in the question number 3, if the norm, if the question says that the norm is 1, the decision boundary parameterization should be 2?
Yeah, so if it says the norm is 1, then there are 2 parameterizations, the positive and the negative. Yeah.
Okay.
And maybe if it says, I don't think we would try to trick you like this, but if we say like decision rule, like the one that classifies everything above as positive and everything below as negative, then there will be 1 parameterization because the negative one is now excluded.
Mm-hmm.
Yeah, but we probably won't try to trick you like that. So good question. Okay, so now I'm going to talk for a bit about some other topics that you might see. There's a perceptron algorithm, which you've saw early on in the machine learning course. So the point of this algorithm is to try to find the linear classifier. It doesn't necessarily need to be max margin, which we'll talk about later. So what you do is basically an SGD style type of thing where you initialize. So you initialize your parameters, then you go through all the data and see if it's misclassified in this way. And you should also understand just why this means it's misclassified. You should convince yourself that this means it's misclassified. And then you perform this gradient descent type of update, except not really gradient descent, but yeah. So you'll have to memorize this. We'd probably give it to you or tell you to refer quickly to your homework or something if we gave this on an exam. But when the data is linearly separable, meaning that you can separate with a line, you will find a perfect classifier in finite number of steps, which, like I said, no guarantees on the margin or anything, but there's no guarantee for non-separable data. So that's kind of conceptually what you need to know. And here's what I was alluding to before, that perceptron doesn't have the concept of a margin. So what's the margin? It's intuitively how close you are to the closest data point, like how close your line is to its closest data point. Right, so this is margin, and as you can see, this purple one has a large margin. It's far away from all the data points, but this orange one is very close to its nearest data point. And perceptron will equally favor each of these lines. So if you initialize at a line, if you initialize with a theta that gives you this orange line, perceptron's not going to do anything because everything's classified correctly. Right, and the intuition here is that, well, maybe this orange line is not so good because what if there are other blue dots that I didn't see that are like over here? Like what if there are dots like this. And I just observed a subset of them that happened to be there by chance, well, then this orange line is not going to do so well. So that's the intuition of margin. And again, so this whole idea is generalization. Do I generalize if my data that I saw was just kind of a small typical set of what I would usually see, but my typical set could be like larger than that, then do I do well on those test samples, even though I did not see them when I was training? So this leads me to another poll, and I'm sending this over here. So I'm giving you 3 diagrams with the training data and a classifier. So the classifier is the line, the training data is the dots. And I want you to tell me if, for each of them, if the classifier can be expected to have a high or low training error and a high or low test error. So by training error, I mean like error on the samples that you see. And by test error, it's you assume that the test samples are kind of drawn from a similar distribution as what you see for training, and tell me if the classifier can be expected to have a high or low error on that data set. I'll give you another 1.5 minutes for this one. Okay, I think I'll discuss this question. So the first question, most of you got right, that the training error, so I'm going to have this thing, training error, and test error. So for one, training error, it classifies everything correctly. So we would say this is low training error. And test error, well, this is what I was alluding to before, that maybe you didn't see maybe you just happen to not see a bunch of these blue dots in the sample by chance, but if you drew more samples, then you would see these blue dots. So actually, you could expect this one to have high testing error, or relatively high testing error. And for the second one, the training error, well, you only misclassify one sample. So I would say that it's a low training error. Your test error, you can kind of assume in these types of questions that the red dots mainly come from this distribution over here. So you might see a bunch of more red dots and you might see more blue dots. But unlike in this first example, the blue dots that you didn't see aren't contributing anymore to your test error because you're far away enough from this original set of blue points that you can generalize. So I would say this is low. And this last one, you guys all got correct, so these are both high. You just can't linearly separate these points. So, yeah, I know that some people have had issues with these types of questions in the past, like wording wise, but basically the gist is that if you see clusters of points like in this left image, and you see like a little straight point over here, then this is like almost always just going to be a question of, okay, they're going to be like, okay, there's this line over here and there's this line over here, which one is better? You almost always want to. So yeah, just don't overthink it, I think. Okay. The question here, how do you achieve large margin for a linear classifier? Well, first of all, you need to kind of figure out what the margin is, right? So in order to find the margin, you need to find the distance from a point to a hyperplane, right? Because you have things like this decision boundary, boundary. I have a point like an x point, and you want to find the distance, right? So if this point x is a point, and then this decision boundary is given by theta dot x plus theta naught. Let's say that this x is now, I'll call it p because it doesn't conflict with notation. Then this line here is going to be theta. So basically one way to derive this is to say, okay, I start from p and I walk tau steps in the direction of negative theta, right? And then I want this to become on the plane. So I want to see how many steps tau do I have to walk. And if you solve this for tau, you end up seeing that this should be equal to, sorry, I miswrote. So this is just saying that the equation is solved, like or p minus tau of theta over theta norm is going to be on that line. So this means that this is going to be, well, let me actually solve this. So you want to solve for tau. I guess this is a transpose. P transpose theta plus theta naught is equal to tau theta, say the theta norm. So then this implies that the tau is equal to P transpose theta plus theta naught over norm theta. And maybe you want to assign distance. So let's just say that. All right, so if this is the distance from a point to a plane, then we can see what max margin classification would be doing. So what that is saying is that we have this decision boundary, right? Let's say we have this sort of decision boundary, right? But we also have a margin boundary, which is kind of slabs over here. So if you sort of add 1 to this 0 instead of, so you want it to be classified, but classified very correctly. So the distance from the decision boundary to the margin boundary is, let's take a point over here, right? So if you have x on the margin boundary, that means that the distance from x to the decision boundary, well, that's given by this formula here, right? Where p is x now. So this would be x transpose theta plus theta naught divided by norm of theta. But that, if you're on the if you're on the margin boundary, then you're this thing here, this thing is plus or minus 1, right? So this is going to be equal to 1 over norm theta. So this is a derivation for that formula you might have seen from that machine learning course, that the distance from the decision boundary to the margin boundary is 1 over norm theta, so that the width of this slab that we're talking about, right, which is the width of, let me find an example. So for example, the width of this slab, so you want the width, or that's a bad color. You want the width of, well, that's also a bad color, but you want the width of that slab. Well, that's going to be 2 over norm of the theta that you use. So we just derived the margin boundary, and then what you're trying to do for max margin classification is that you want to maximize this width subject to being correct everywhere past the margin boundary. So my note here is that large margin means that you have a small norm of theta. So if your data is not linearly separable, then you can soften this constraint. So before we just saw a hard margin version where you say everybody needs to be classified, let's say very correctly, greater than or equal to 1, right? Now you can say, okay, you don't have to all be classified correctly, but you will pay a penalty by this norm of theta. So if you notice here, large lambda is says that this theta norm term makes more of a difference in this objective. So if your theta lambda is large, then you're going to want to have a smaller norm of theta. And that means that you want to have a larger margin, right? Because having a larger margin means having a smaller theta here. So small theta, large margin, large lambda. So very quick poll. Let's see if I can paste it into chat. Oh, my computer's glitching up. Hold on, I will be back. Okay, I'm back. Sorry, my computer just glitched out. It does that. Did I manage to send the poll? I think I did. So I believe I sent a poll that's called regularization, yes. So please send that, fill that one out. It should be quite quick. 15 seconds. Okay, actually, I think we have everyone. Maybe not. 5, 4, 3, 2, 1. Okay. Interesting. Okay, so this one seemed like a contested question, so I will reiterate what I said here. That okay, large lambda means that when you do this minimization objective here, this minimization objective, right, here you're trying to minimize misclassifications, but you're also trying to add, you have this regularizer. So when lambda is large, this makes a lot of a difference. So you're going to want to pick theta that has a small norm, right? So large lambda means small theta, small norm of theta. But what did I say from before? Large margin corresponds to this small theta, right? Because the width of the slab, which is like your margin, is 1 over the norm of theta, right? So if you have a small theta, you have a really large margin. So this means large margin. So the question is, which one of these lines has a large margin? And in fact, it is the purple line that has the larger margin, right? So purple has larger margin. Because the orange one, it's like barely any regularization at all. It should be like a small lambda because it's so close to those points. And yeah, so it has a very small margin. Like imagine the margin here is like this small versus this margin. Yeah, so if anyone has any questions on this, they should ask. There will very likely be a question that looks something like this. So yeah. Okay. I'm going to go quickly through this because it's kind of a simple message. So you can use kernels to make fits that are not linear, right? Where kernels, it's basically some magic that allows you to rewrite a class of rewrite some sort of algorithm in a way so that you can use a nonlinear function, right? So this is mainly what you need to know, that the kernel method can give you a nonlinear fit. And how do you do that? Well, there are different types of kernels that can give you different types of fits. So quadratic kernels, for example, say that you have like plus, 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 and then negative, 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 like this type of thing, right? Well, a quadratic kernel can give you something that looks like this, right? So you can use a linear classifier in this case, but you can also use a quadratic classifier. So regularization works in the same way, or in a similar way, let's say, that in principle, you could have like a quadratic classifier that looks like this. So this one, according to what we said from before, would be a small lambda classifier, basically. Small lambda, because there's like, it looks like there's very little regularization on it. It's very, very close to the points. And this purple one seems to have a larger margin in some sense, right? So this is quadratic. Let's say quadratic. So cubic, you can do similar fits. Like now instead you have, like maybe you have this, and then this. You can do a cubic fit now. So that's like this, right? Maybe like that. That's a possible cubic fit. So now you can have basically 2 bumps. You can do more squiggly things the higher order of a polynomial you use. And then RBF, which is radial basis function. Just think of that as you can fit basically anything that you want. So if I wanted to fit a classifier that like, if I say like a bunch of blue points, and then I say, actually I'll just do plus and minus like I've been doing before. If I have a bunch of pluses and I have a bunch of minuses, then the radial basis function, you can think of it as just basically saying I am capable of saying that everything within these little circles is plus, and everything else will be minus. Like I'm capable of doing such a very complicated and non-smooth fit. So you can basically do anything you want with those. That's the main idea. Okay, linear regression, I'm not going to cover it today. I don't have time to study it for the statistics exam because you will probably need to know it. But it's the same principles that you have this loss function, you can regularize it, and so on. Hyperparameter tuning, a quick remark. How do you find lambda? The standard thing to do, well, you can either have a training and validation set. So you have two sets. You train on the training set. You test on the validation set to see which of your models was best, which lambda value was the best, and then you choose the lambda with the best validation error. Right? Cross validation, I'm not going to really write too much about it, but you can read about it in the course again. It says that in order to make a validation set, if you don't have a validation set like already, then divide the data set into like k partitions, and then say, okay, for the first iteration, I'm going to take the first k-1 and train on those k-1, and then evaluate on the last held out partition. Then I'm going to take the first k-2 and the last one, and then reiterate and so on. So you can read about that. I'm not going to really talk about it in too much detail right now, but it's something you should conceptually know. And you cannot use the test set to decide your hyperparameters. If we ask you a question and you say, can you use the test set to decide your hyperparameter? The answer is no. Like don't do anything with the test set that will involve you retraining your model, because that's not what's supposed to be used for. Okay, so we are halfway through, and of course I have not even covered that much of my material. So the good thing is that these slides, I will be providing them to you. I will be sending them out after this session. So it's not a problem if we don't cover everything. So you need to know the different types of neural networks and probably some of the applications and limitations of these neural networks. So kind of basic things like, why would you use a feed-forward network? Why would you use a convolutional network? Why might you use a recurrent network over a convolutional network, and so on. And you might also need to know some backpropagation. So that's how you train a neural network, by taking derivatives. Right? Okay, so this is an example of a feed-forward neural network. What you do here, just to remind you, you have all these neurons that are inside these little circles are called neurons. And they represent the output of a function, right? So this whole thing represents this output here. This last neuron represents the output of this whole neural network. This guy represents the output of a certain subnetwork, and so on. So formally, how we write this? Well, okay, what the thing that goes into this, let's call this neuron 1, 2, and 3. The stuff that goes into it is equal to, well, x1 times w1 plus x2 times w2 plus some bias term b1. Right, so that's how you read it. You kind of multiply the this W1 times the output of this neuron. And this neuron outputs X1. Right? So you also have outputs, so there might be some function H, which is the activation function, that's what they call it, which operates on the input of a neuron and it gives you an output. Right? So this is sometimes the sigmoid output function, sometimes the ReLU function, and hopefully these are familiar terms. Then what do you do? So you keep on iterating this. So for example, here we have in2 being the W3 times the output of the first neuron, so out1 plus the bias term B2. And then you can define out3 or out2 as the same way as the H of the in, and so on. So in an exam setting, we would probably give you some sort of definition, like some sort of notation that might look like this. We'd be like, okay, let in2 be the input to neuron 2, and so on. Like, then we probably want you to compute the output of a network, or compute the gradients of some sort of parameters, and so on. So, yeah, I have a question on this here, but I will probably not go through it right now because it's a little more computation than I think we have time for. But basically, evaluating the neural network is how I described it just now, and you should review that. You should be able to do simple ones by hand. And just to recap, if you haven't read the rules for the capstone exam, then I think you can use Python, but you are not required to. And you can use a simple calculator. So whatever we give you probably won't require like crazy computations. It should be something that you can do pretty easily. So there won't be like super involved calculations, I think, on the exam. Okay, so gradient descent, I've mentioned it before, but the rule here is that you update by subtracting a step size eta times the gradient of the loss, right? So that's how you minimize the loss. Find good parameters that will help you minimize the loss on the data. Right, so here I'm just putting the notation again here, this notation for the in and out. And backpropagation here would say, okay, we're going to use the chain rule in a systematic way, and that way is going to help reduce the computation time of finding the gradients. Right, so just as a primer, like here we have, remember we had, let's say out 4. This would be H of in 4. And then in 4 would be, what would it be? It would be W5 times the output of, this is 1, 2, 3, 4. Let me relabel. Out 2 plus W6 times out 3 plus W4, right? So how can you find a, let's say, derivative with respect to W5, right? So if you want to find a derivative of out 4 with respect to W5, so say, let me write the more pleasant looking color. The out 4 with respect to dW5. Well, actually, this is, you could write the whole thing out, like write it all out and then compute manually the derivatives, but you can also do this chain rule type of thing where this is equal to the derivative of the out 4 with respect to in 4 times the derivative of in4 with respect to w5, right? And here we can see, okay, the second term here, in4 with respect to w5, that's easy, it's just linear in the output here, out2, right? So, bad use of board space, but this is going to be out2. And then this guy, d out4 or d in4 would just be h prime of in4. Right, so in this way you can systematically break down the gradient computation. Because this thing is defined so hierarchically, it's like functions upon functions upon functions. But that means that you can use the chain rule to kind of simplify your calculations. And what they do in this is that note that this gradient uses the output of the neural network, right? So what they say is, okay, your forward pass, you compute all these ins and outs, and then your backward pass, you use these to compute these gradients. And then from there, you can just update all the parameters. Right, so yeah, so you should know how to apply this chain rule type of thing. If we give you a question on it, we might either ask you to compute like with numbers, or we might ask you to like have some symbolic representation. Like we might give you a multiple choice question, say like which ones are expressions for the gradient of this, and so on. So the more complicated case here is that if here, like I wanted the effect of W5 on the output 4. What if you want, okay, so the loss here, you want the effect of B1 on the loss, right? Well, here B1 affects the loss like through this path and through this path. So you actually have to account for both of these paths. But it's not much more complicated than this. So then, like I say here in our quadratic example, you can evaluate this dn over db3, and you can basically just evaluate things systematically and break down the computation. So that's the whole point of using the chain rule, and that's what constitutes backpropagation. Okay. Again, in the interest of time, I think these ones, I think it's just good to maybe find an example from an old class, from your old class notes, and just make sure you can follow it, make sure you can do those calculations. And you can look at these questions that I'm skipping over during, after the review session. I'm just skipping over because it's maybe a little more time than we have. Okay. And of course, as usual, let me know if there's any questions. Otherwise, I will continue on to the other types of neural networks. And these are ones that we cannot necessarily test you so much on, I think, in some sense that like they're a little more complicated. So I don't think we'll really have big problems where you need to take gradients of these guys, because sometimes it can be a little complicated. If we did that, it would be like a very simple case. But the conceptual part of these is more important, because those ones we can like maybe ask you a multiple choice question, and just to test that you know how these are used. So for example, these are convolutional nets. One reason you might use a convolutional net over a fully connected network is that you have much fewer parameters, right? So fully connected networks, the number of parameters, like if you have a D1 vector and you're transforming it to a D2 vector, the number of parameters is the multiplication of the two. So if you have an n vector turning into n vector, that's n squared parameters, right? Well, convolutional nets can use a lot fewer parameters, and the way they do that is by assuming there's some sort of spatial locality in some sense, that you can create features that are shared as you slide a certain window across this whole grid. So what that means here is that you usually have an image, right? And then what a convolutional network does is that, okay, it takes what's called a kernel, say like a k by k kernel. Maybe this is a 3 by 3 kernel. It computes the dot product of this kernel with the image, right? And it sums up all those the multiplications, right? So you just take the dot product of the kernel with this image segment, and that gives you the first slot of this new image, which is going to be smaller. So that's over there. You slide the kernel by one step. It's really hard to draw, but I'll try. Take the dot product, and then this guy now goes into the next slot. And then you just kind of keep on doing that, right? And you can do this with multiple kernels. The whole point here is that now these kernels, like this one has only 9 parameters, right? But you're incorporating information about this whole image into the new image that you're mapping to. Right, so you can use a lot fewer parameters in these convolutional nets, and that's giving you like a feature representation for what you can do further like neural networks. So you can, like, if you have a small enough resulting image, you can then flatten it and then do a fully connected layer. That's common. So you might need to know how to count the number of parameters in a convolutional net, and I recommend just knowing the formula, write it down somewhere, put it on your cheat sheet. It's here, not much insight to say about it. When you have a certain stride, which means that the kernel can slide by a number that's not 1, then that'll affect how much you reduce that image. And if it wasn't clear, the reason why you're reducing the image is because, like, you have a kernel, and like when you slide it over, there's some you're not sliding it over like m times for this m by n image. You're just kind of sliding it by m minus k times. So that's why you're going to reduce the size of this image when you're doing this type of thing. So that's the main thing that you need to know about these convolutional networks. Use them usually for images, like helps when there's some sort of spatial features that you want to capture, and you can also compute these number of parameters. So recurrent neural networks are another thing that there's a lot of facets to them. Sometimes you can make them very complicated if you want. What you need to know here is that they're used for sequential data, and the example that's often given is speech, text data, and so on. So usually what you're doing is you're encoding a sort of sequential data into a vector, and then you can use that for further tasks, such as using that vector to predict the next word of the sentence. So high-level conceptual things that you might want to know. Well, this network unrolls. So, like, for example, if you have a sequence that's like a cat ate the mouse. Right, so this can kind of translate to sort of having like 5 different layers of a recurrent neural network. Like 5 layers basically. Right, but these layers will share some sort of parameter, and you can see that from the equations if you go back to your the class notes on the recurrent neural network. So another thing you know is that there are ways to incorporate memory and mitigate your vanishing gradient problems. So vanishing gradients, when you train, sometimes the derivatives can go down to 0 as you increase the number of layers in your network. So there are ways to mitigate that, and like LSTM is one of them. So that's kind of what you should know. Like, know what this is, know what the purpose is. Those should help you for the conceptual questions on the exam. And it's possible to overfit neural networks. The methods are kind of the same, so I won't really go over this much in this section right now. So, but you can read it on your own. Okay, so we're finally done with supervised learning. Now let's go to unsupervised learning. So the main topic that we give you in unsupervised learning is clustering, right? And we see some different ways to do that, which are all kind of variants of the k-means algorithm. So what k-means does is that you say, okay, I start with some initialization of the cluster centers. So I have data, like data over here, and then maybe have data over here. Remember, this is unlabeled data. So maybe I start with like mu1, mu2. Then what I do is I repeatedly say the following, okay, find which cluster each element belongs to according to the current clustering. So, well, maybe here's some of these, because this clustering is not very good. So maybe, all right, maybe like this guy belongs to mu2. And maybe this guy also belongs to mu2, and then the rest of them belong to mu1. Right, then I compute the mean of these clusters. So that'll shift these mu's. So then this mu will maybe shift over here. This mu will maybe shift over there, kind of hypothetically. And then you keep on reiterating that until things stop changing. So it is actually true that at some point, eventually, in finite time, I think that your clusters will stop changing. So if you run it long enough, you will stop changing your clusters. You can also use heuristics like stopping at some sort of max iteration value. So k-means the formulation is nice. One of the things that is more testable, I suppose, is what kind of problems that there are with k-means. One of them is that you have local optima. So this makes it dependent on initialization. When I say local optima, it means that the mean square objective is has some local optima, so that you can get stuck. So k-means will stop doing anything, but like it won't actually have a good clustering. So it results in clustering not looking good. Looks bad. Other problems, it doesn't really scale automatically to non-Euclidean metrics, which just it's sometimes you might want to use a different metric. And this Euclidean nature makes it very sensitive to outliers. So, Euclidean stuff like L2 norms and just regression that does not have like a median or lasso type of regularization, like that will be sensitive to outliers sometimes. So an alternative here is to use k-medoids, right? And what that is that instead of doing k-means regularly, you have to require that each cluster is actually a point in the data set and not just some random like location out there. So here, like you wouldn't start with mu1 and mu2 out here. You would start with them like each of them is a point in the data set. And that can actually make you more robust to outliers. Okay, so this is a question that I am going to do because I've been talking for a very long time. So let me send you the poll, but what this question is asking is that, okay, I've run k-means. I've run k-means for a while, and I found that it looks like I've converged, but my clustering looks very bad. So how can what can I do to try to get a better clustering? And pick all that apply. Okay, I'm getting a lot of responses. Oh, the initialization point is part of the data. It doesn't need to be part of the data. Maybe for k-medoids, you would initialize it as part of the data. So okay, yeah, let's say it is part of the data. Say 20 seconds. Okay. I think I will go over it. If you want to finish up and put your response down, that's fine. Yeah, so most of you said that the last two are valid options. So let me write that down. These last two. So this is correct that these last two are valid options. So you can restart from a new random initialization, and this is what's common in practice. You just take a bunch of random initializations and you restart. Right. 4, you can restart from the same initialization but use k-medoids instead. I didn't tell you anything about the data. Maybe there's some sort of outliers in the data that make you make k-means not work well. So maybe k-medoids could work potentially. I haven't really told you anything, but there's no reason to say that it would not work. Right, so that's a valid option. 1 and 2 are not valid options, and you might notice that they will actually give you the exact same result. So, for example, if you continue to run for 1,000 iterations, well, I found the cluster assignments stopped changing, so I've actually converged. So running 1,000 more iterations is not going to do anything. And restarting from the same initialization just isn't going to do anything either because there's no stochasticity. There's no randomness here. So that's why I need to have something different. This gives me a new initial condition that I can try. Okay. Very good. Let's talk a bit about generative models. So generative models, the main generative model that we talk about is Gaussian mixtures. So what do we want to do with generative models? We want to model how the data is generated, right? And then from there we can, if we want to do prediction, we can try doing that. So in this case for a Gaussian mixture, like you have this stuff over here, and then you have this stuff. You have a bunch of points over there. Right, it looks pretty bad. I don't know why I keep on drawing dots instead of pluses and minuses, but you can model this as a Gaussian mixture, right? So maybe there's a Gaussian over here, and then maybe there's a Gaussian over here, right? Then if you know this mixture structure, you can take a new data point and try to pinpoint it to which cluster it was in. So that's what clustering is. I'm going to erase this drawing because it's not very pretty. But yeah, so I want to do a quick example about that kind of shows you the math that shows you the form of a decision boundary, right? So my setting here is that I have a random variable z, which is going to tell you the identity of a point. So it's going to tell you if the point is in the negative mixture or the positive mixture component. So right now I'm going to say it's probably 1/2 each. And this x, which is the covariate that you see, is going to be -1, or it's going to be normal where the mean is equal to z, right? So if z is negative, it's going to be centered at -1. If it's positive, it's going to be centered at +1. So you don't get to see the z, but you can see the x's. And I give you the formula for this normal density. So note here that the identity matrix is the shared covariance. So both of these components have the same covariance. So this mixture basically looks like this. -1 and +1. So this is what the mixture looks like. So when you cluster a new data point, in order to cluster a new data point, you want to tell me what z it came from, right? So I see a new x and I want to find the best z that fits it, right? So that means I want to find the cluster I that maximizes the probability of that cluster given the data, right? So I want to find the one that's the best fit for that data point. So how do we find the form of the decision boundary? Well, basically, decision boundary is that decision boundary is the x, the set of all x for which this probability of 1 is equal to probability of -1. Right. This is the point, the boundary where I'm uncertain about what to classify as. So how do you do this? You can note that probability of z given x, it's proportional to probability of x given z times probability of z, right? And this is given by Bayes' rule. If I remove the proportionality, it might confuse you, so let's remove it. This is equal to this divided by probability of x, right? But if I'm going to be comparing these two quantities up here, then probability x is going to be the same for both of them. So it'll cancel out. So basically what that means here is that at this decision boundary, probability x given z of x given +1 times the probability of +1 is equal to probability x given z of x given -1, probability of -1, right? So let me just call this alpha here. So probability z, define probability z of +1 equals alpha. So this gives me that this guy is alpha and this guy is 1 minus alpha, right? So if I write down this this guy, right, because this, I know the distribution now, it's going to be normal. Essentially what I get here is e to the -1/2 x minus mu squared. What's mu? Mu is 1, right, for this distribution, times alpha is equal to exponential -1/2 x plus 1 squared times 1 minus alpha. So let me take logs on both sides because it makes sense. These are a lot of exponentials here. I can take logs to simplify it. So that means that I'll write the log term alpha. So remember the logs product is the sum of the logs. Log alpha plus, say, minus 1/2 x minus 1 squared is equal to log 1 minus alpha minus 1/2 x plus 1 squared. Right, so I'm almost running out of space here, but remember that x minus 1 squared, like norm squared, is equal to norm of x squared plus some linear function, linear in x, right? I could write it out what the other part that's linear in x is, but you can see here that, yeah, if you expand it, the only quadratic part is x squared, right? But that's kind of the same thing for this too, this term. So this term is x squared plus linear in x. This term is also x squared plus a different linear in x, right? So if I rearrange on both sides, I end up saying that log alpha, say minus log 1 minus alpha is equal to 1/2 times, let's say, x squared plus linear, let's say linear 1 in x, minus 1/2 times x squared plus linear in 2 in x, right? So which x satisfy this? Well, this is the interesting thing about this particular shared covariance structure, that this x squared, this 1/2 x squared, cancels out with this 1/2 x squared. So ultimately what I see is that this is going to have a linear decision boundary, because now the only terms that are remaining here are just linear in x, right? Okay, so now a quick poll. Yeah, so this quick poll says, okay, what about if z has a prior probability alpha instead of negative 1/2 and 1/2? Then is my decision boundary linear, or is it quadratic, or what is it? And I'm going to be putting the link in the chat, but think about it for a bit. Okay, so this is a quick poll, and I'll just show you this previous slide just for reference. So I'm thinking maybe 2 minutes for this one. About 15 more seconds. Okay, let's go over this one. So, I'm gonna try to repaste what I had before. So, I think maybe it'd be better if I actually write this out instead of being lazy and just writing linear in X. First of all, I realize that I'm working with scalars here anyway, so I'll just have these as not norms, but just scalar squared. Right, so if I really just expand this out, then I get 1/2 x squared minus 1/2 times, well, what's the rest of this? It's going to be negative 2x plus 1, I think, right? Equals log 1 minus alpha minus 1/2 x squared minus 1/2 times 2x plus 1, I think, right? So you notice that these red terms disappear, they cancel out. I'm left with log alpha minus 1/2 negative 2x plus 1 equals log 1 minus alpha minus 1/2 2x plus 1. So if I simplify this, this actually gives me the, if I can do math, this gives me 2x here on this side equals log 1 minus alpha over alpha. So actually, this is still a linear fit, right? So the decision boundary before, like if you plug in alpha equals 1/2, this right-hand side would just be log 1, which equals 0. So that would become 2x equals 0 if alpha equals 1/2, right? And that's the parameterization of the linear fit 2x equals 0. I'm working with only one dimension here, but the moral of the story is the same in higher dimensions. So here, this doesn't actually change the, it doesn't result in a quadratic dependence on x squared, on x, for example, right? Like if I had a quadratic thing like x squared here that remained after I did all these cancellations, then it would be quadratic fit. But actually this is still a linear fit. It just changes the bias, like bias term of the linear fit, right? So point of the story is that this is a linear decision boundary. Okay. Cool. There's a whole lot more about, well, not a whole lot more, there's some more stuff about generative models, like how to estimate them, and that's tied to the MLE and using the EM algorithm. So hopefully these are abbreviations that you are familiar with. I'm not going to talk about those today, and the EM algorithm, like, I know it looks really annoying and complicated, but I think you should maybe, for this one, look at the mixture of Gaussians examples that we had back in the machine learning course, and just make sure you can follow them, make sure you can, derive the updates and so on. So I'm not going to go over it right now because we have 15 minutes left, and there's a little more that I wanted to talk about, which is reinforcement learning, right? So RL, there will probably be a question on the exam, as I mentioned. So just to recap, what are we trying to do here? We are typically given an MDP, which is a Markov decision process. It kind of shows how the state of the world works. So usually the example is that you have some sort of agent, like maybe a robot. He's moving around in the world, and he gets rewards every time he goes somewhere, right? Maybe the rewards are negative, maybe they're positive. We just call them rewards, right? So, and there's like maybe some potential randomness in how he moves. So this is all formalized by the Markov decision process. So states, like maybe where the location of the robot, actions, which is like moving left, right, up, down. Yeah, transitions, which say, okay, you take a certain S and an S prime and an A, right, an action A. So I take the action A from S, I arrive at S prime. Yeah, so what's the probability that I actually arrived at S prime? Because maybe I can try to take an action, but I might not be able to deterministically get to where I want. And you have rewards, which are basically you're going to be trying to seek the best reward possible. So a robot might say, okay, I've gotten a reward if I'm able to fold the laundry correctly, because maybe my task is trying to fold laundry, and I'm a robot. I want to get the reward, right? So here, like S prime would be maybe the state of like having your laundry folded correctly. Like once you reach S prime, then you can get a reward. So you can associate a sequence of actions with a discounted reward, and this kind of just says, okay, maybe maybe the sequence of actions, you want to associate reward with the sequence of actions, but you don't want everything to have equal weight in the assessment of your reward. So things that happen further out, maybe they don't get as much weight in your total reward. So this is what discounting is, and the main thing here is that basically you can find optimal policies that allow you to pick the best action for any given state. That's the main idea. So what do I mean by that? Policies are functions from states to actions. It tells you what to do when you're at a given state. And value functions, so there's a value function which tells you, okay, start at state S, what's the best possible expected discounted reward that you can get overall policy. So like, take the best policy from S, what's the best you can do? And the Q function is a related function that says, okay, it actually takes in an S and an action, right? So you start at S, you take action A, and then after doing the optimal thing for all eternity, what's the best expected discount reward you can get? So from properties of this Markov decision process, you can derive these types of formulas. So one here, this value the value is basically choosing the best action and putting it into the Q function. Right, that's kind of just by definition. This Q function, well, based on the Markov property of this type of process, where you're assuming that transitions don't affect or aren't affected by what happened before, they only affected by where you're at right now. From this, you can actually derive the Q function in terms of the other parameters of this Markov decision process. And then you can plug in this second equation into the first one, and you get this sort of fixed point relation, right? So whatever the value function is, it has to satisfy this thing, which also depends on the value function, right? So just to recap here, remember that the value function here is the best reward you can get once you start at S. The Q function is the best thing that you can get when you start at S and perform a certain action. These give rise to these formulas, and now my question to you is, actually, I told you I wanted to find optimal policies, but I gave you, maybe I know the value function and I know the Q function. So how can I actually extract an optimal policy from these value and Q functions? So I would like you to spend a bit of time to fill this poll out. Okay, how about maybe one more minute? Okay, we'll discuss it. So let's see, the first one, is this an expression for pi star of S? No, it's not, because this is the value function, but it doesn't even have the right range, right? So the value function maps states to, let's say, real numbers, like the rewards, right? But that's not necessarily the action space. So this is not correct. What about this one? Second one, max of Q star of SA. Well, that one's close, but that also does not map you to the correct space. This maximum map gives you the value, or like, yeah, it gives you the reward that you would associate with the best action, but doesn't give you what the best action actually is, right? But this one, 3, does actually give you what the best action is. It tells you just by definition that that like the best thing to do is to maximize the reward that you get after performing the action. But the reward you get after performing the action is exactly Q star of SA. So that's why 3 is correct. And 4 is also correct. And why is that? Well, it's just plugging this in actually. So I gave you alternative formulas for the max here. So if you place an argmax here and then you place an argmax here, you get the exact same thing. So this is just another, this summation is just another definition of Q star. Or well, this maximization is just a definition for the maximum of Q star and so on. Okay, so there's this computationally annoying thing called value iteration. By computationally annoying, I mean that sometimes it's annoying to do it by hand, but you need to do it. So what is this thing? So you have this fixed point iteration now, right? So we said that the optimal V star satisfies this equation with equality. So if you're given an initial estimate of V star that does not necessarily satisfy this equation, well, you can say that, okay, I'll have a new V star, and I set it so that if I put this new V star, then it satisfies this. So this new V star is going to satisfy this equation, but with this old V star plugged in here. So then hopefully if I keep on doing that, I'm going to end up with something that satisfies V new star equals this thing with V new star over here. And that's exactly what I've outlined here. So first you initialize, you usually might just initialize to 0 because you don't know anything about the values. Then you repeatedly say, okay, for each iteration k, and then for each state, you're going to fill out this corresponding entry of what v should be. So vk is going to be this maximization here. So you basically take the best action given the reward that you have plus the discount factor times the value that you found in the previous iteration. So I have an example here, and I know there's not much time left, but I'll just kind of go quickly over here. So what do you do here? We like to represent these things as a value, as a table. So you might have this green, good, bad. So these are good and bad states. What you have here is that, I guess I didn't describe it, that you have a deterministic dynamics. So you can choose to go up or left or down or right, and you will always go the correct direction. And you obtain rewards, and your reward is going to be 10 if you started off at green, and negative 10 if you started off at red here, which is the bad square. And otherwise, you will obtain 0 reward. Right. So here, say N1 and N2. So V0, say V0. According to this algorithm, we start everything at 0. So V0 of S, and then, so each of these guys on the top is S, and then we're going to fill out this table. So this would be 0, 0, 0, and 0, just from the beginning. So V1 of S, when we're at the good square, right? So we're at the good square, and then we want to basically compute this equation, right? So we're going to look for every action that we have and compute this reward. So this deterministic dynamics here means that this thing is not going to really matter. You just pick the actions that are possible. So here our actions that are possible are left and down, right? So if I go left, then I get a reward of 10, because that's what I said here. You get a reward for leaving the good state. So I get 10 plus gamma times this factor, well, nothing, according to vk minus 1, nothing had a value, so this would be 0. And it'd be the same for if I move downward, so I'm just going to say this is 10, right? If I'm in the bad state, then no matter what I do, I get negative 10, right? And even if I move to this good state, well, my previous value function doesn't know the good state is good, so it's still going to give you negative 10 here. So from the same logic, you can see that this is 0 and 0. Then I know we're basically out of time, but I'll just give you a quick example for how you might do this. So suppose you're at the good state now. Let's do this good state again. You can go here or you can go here, right? Well, if you go here, it says you get 10 value plus gamma times the value that you found previously for n2, but that's 0, right? So maybe if I go here, I can get 10. If I go here, then I get 10 plus gamma times the value of being in state B at step 1, right? But that would be negative 10, right? Times negative 10. So that's less than 10. So I would not want to go to the bad state, which makes sense, right? So your value would still stay at 10. And now for if you're at the bad state, well, if you're at the bad state, then if I go left, I can go to n1, but I still have negative 10 reward. If I end up going to the good state, well, now v1 knows that the good state is good, right? It has a positive entry here. So actually, if I go up to the good state, I get negative 10 plus 10 times gamma reward. So this is how I would start to learn that actually maybe if I'm at the bad state, I should go up instead of just doing a random thing like going left. And you can continue to fill out this table for N1 and N2, and you should do that on your own, just as an exercise. So this is pretty much it actually. There's other stuff like Q iteration, but it's really kind of the same deal. If you can do value iteration, you can probably do Q iteration. It's really just the same algorithm. And there are other aspects of RL like sampling when you don't know the dynamics. So you should probably study up on those, but those might just be a quick conceptual question. Maybe not so much of a fully fleshed computational one. But definitely know how to do this value iteration, know how to do the Q iteration, and so on. Okay, so that's actually all the material that I have, and I will be sending out these slides, and we'll probably annotate them and like have those questions that I did not tell you. I'll probably put some solutions to those as well. And yeah, so good luck on the exam. Study hard, study well, and take many breaks, and so on. So yeah, thank you.
Thank you, William.
Thanks, Wei.
Thank you to
Thanks.
you, William.
Thanks, William.
Thanks for coming.
Thank you, William. See you.
Thank you, William.
You guys, good luck.